This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, I am covering the topic thick cylindrical shell in mechanics of solids. The cylindrical shells having several applications in engineering field, such as transporting or storing of liquids, gases, as well as the fluids. In examples, they are pipes, boilers, storage tanks. These cylinders are subjected to fluid pressure when it is transporting gases or the liquids or storage. When a cylinder is subjected to an internal pressure, at any point on the cylindrical wall, three types of stresses are induced in it. These three are mutually perpendicular to each other. These three are, one is the Hooke stress, it is also called the circumferential stress. The second one is longitudinal stress, and third one is radial stress. Hooke stress or circumferential stress. This is directed along the tangent to the circumference of the circle as shown in figure now. This is known as here now, this is the elevation of the cylinder or the circumference of the circle, that is the front view of the cylinder. In this case, the stresses are acting as perpendicular to the tangent to the other circumferences as shown in figure. Because of the stresses, the tensile in nature that increases, or in other words, the diameter of the cell increases. The second one is longitudinal stress. This stress is directed along the length of the cylinder. Because of the cylinders, because of these forces, it is now divided into two parts. When the pressure exceeds to the maximum values, the nature of the stress is again in tensile. Because of this longitudinal stress, the length of the pipe or the cylinder increases. The third one is the radial stress. It always acts in opposite directions in which the pressure inside the cylinder is acting. Generally, the pressure is acting radially upward directions, and radial stresses are acting towards the inside of the cylinder. Hence, these are in compressive nature. These three types of stresses are induced in the cylinders when it is stored with the fluids as well as the liquids or the gases of high pressure. These cylinders are classified into two types now. One is known as the thin cylinder, another one is known as the thick cylinders. The thin and thick cylinders generally is classified based on the ratio of T by 20, which is equal to the thickness. When thickness is here less than the values of D by 20, if it is equal to 0, if it is equal to less than D by 20, or in other words, T is nothing but less than 0.05 T, then it is known as a thin cylinder. If it is a more values, it is known as a thick cylinders. Here a cylindrical shell, which values D by 20 values is less than 0.052 is called thin cylinder. In case of thin cylinder, the radial pressure is very, very small now, hence it is neglected now. But in case of thick cylinders, the magnitude of radial stress, that is PR, its value is large, and hence it cannot be neglected. It is considered while calculating the stresses that are induced in the cylinder. Here, thick cylinders introductions. The thick cylinder is the thickness of the cylinder is large when comparing with the thin cylinder. This is based on the ratio of, that is the T is, if it is more than D by 20 values, then it is called thick cylinders. The magnitude of radial stress, PR, is large, hence it cannot be neglected in case of thick cylinders. When a fluid is subjected within the cylinder, three types of stresses are induced. One is radial, second one is circumferential, third one is the longitudinal. The radial pressure in the case of thin cylinder is neglected, but in the case of thick cylinder it should be considered. And it is in a compressive nature. The circumferential stresses, it is also not uniform along the thickness of the wall now, and it is having in tensile nature. The longitudinal stress, it remains constant throughout the thickness of the wall. So third one, the radial stress is in compressive in nature, and the circumferential and longitudinal stresses are in tensile in nature. The radial stresses and circumferential stresses are generally computed by using Lami's equations, and the longitudinal stress is almost uniform throughout the thickness of the wall. Hence, it can be neglected here now, but considered for computing values. But here, these two values, that is radial stress as well as circumferential stresses, are computed by using assumptions of Lami's equations or Lami's assumptions. So, Lami's theory, the problem of thick cylinders, generally they are complex in nature. They are determined by using certain assumptions made by Lami's. These are called Lami's theory or Lami's assumptions. The first one is the material is homogeneous, isotropic, and obeys Hooke's law. That is, the stresses are within the proportional limit, and isotropic means the elastic properties of the material is same in all directions. The plane of the section of the cylinder normal to its axis remains plane and normal even under pressure. The longitudinal stress sigma 1 and longitudinal strain epsilon remains constant throughout the thickness of the wall. Since the longitudinal stress and longitudinal stress are constant, the following the difference in magnitude of offset and radial stress PR at any point of the cylinder, it remains constant. Okay, based on Lami's theory, here the determination of circumference stresses as well as the radial stresses induced in the thick cylinders. For determination, let assume just R1 is representing the outer radius of the cylinder. Here, this is nothing but representing the circumference of the cylinder. R1 is representing the outer radius of the cylinder. Similarly, R2 is representing the inner radius of the cylinder. Here it is equal to inner radius is given, and L is representing the length of the cylinder. It is there like this now. Now consider an element ring of the cylinder, thickness dx, and a radius of x as shown in figure now. Here we are considering this is center of the circle. Here we are considering this ring which is represented here now in blue color, which is at a distance of x, that is radius equal to x, and thickness is equal to dx now. On this ring, let Px is representing the intensity of pressure on inside the ring. Px is representing, here it is given, representing that is the intensity of a pressure on inside, and Px plus dpx is representing the intensity of the pressure is outside of the ring, and sigma x is representing the intensity of Hooke's stress induced in the ring. These are we are now considering now. The bursting force on any longitudinal section, same, just xx is equal to bursting force. Here when we are considering now, that is the pressure is acting just inside it now. On this wall only we are considering now. Here now having thickness which is equal to is given px into 2xl now bursting now. Here pressure is given, here the diameter is given x plus x 2x, because just nothing but we are considering entire its length like this, that is x plus x 2x into L, that is known as 2xl, that is the bursting force acting is inside the cylinder. But outside is given now here px plus dpx into 2 into x plus dxl now. Here the difference of these two pressures inside as well as the outside that gives just bursting force on the longitudinal axis at a distance of x from the radius having thickness dx ring now. So the bursting force is equal to px into 2 into xl minus of px plus dpx into 2 into x plus dx, which is shown in figure equation number 1 now. But here resisting force is there now. Sigma x is representing the intensity of the hoop stress now. So 2 into dx into L now, because the resisting force is nothing but only the thickness is there now. On both sides we are taking. That is dx plus here dx to dx. Again this entire length we have to consider now. Hence it is equal to sigma x into 2 into dx into L, which is shown in figure number equation number 2 now. Here the bursting force as well as the resistive force both are equal when it is about to burst, that is in equilibrium. Hence equating these two equations now we got sigma x into 2 into dx into L is equal to px into 2 into x into L minus of px plus dpx into 2 into x plus dx into L. So in these equations now, entire equations, 2 that is the here coefficient it is there, L that is the length that remains constant now. Just remove these terms from that equations, but the remaining equation can be written as now sigma x into dx is equal to px into x minus of px plus dpx into x plus dx now. So from this relation we got sigma into dx is equal to here px into px it is there now. On expanding these equations, px into x, px into dx is there. Again now dpx into x minus of dpx into dx is there now. That minus sign is there. 1, 2, 3, 4 terms it is having minus sign. Here just px into x both are equal in magnitude having opposite signs, they get cancelled now. The remaining values is there minus of px dx minus of dpx into x minus of dpx into dx now. So from this relation now dpx is a very small now, the pressure changes is across the thickness and thickness is also dx very small now. The product of dpx into dx that can be neglected now. Hence that remaining values are now minus of px dx minus of dpx x divided by dx now, because just I am taking sigma x is equal to here it will come. From this relations we got to minus of px minus of x dpx divided by dx now. According to the assumption, this is nothing but equation number 3 now. According to the assumptions of Lem's theorem, the longitudinal stress as well as the longitudinal stress that are remains constant across the length now, that is thickness. Hence, it can be written as at any point at a distance of x from the center, the 3 principal stresses are acting. Already we considered these are the 3 are there. They are radial, hoop as well as the longitudinal. The longitudinal stress at any point is given by longitudinal strain at any point is given by. You have to consider the effect of radial as well as the hoop stress. This that is comes under now lateral strains now. So the total strain is equal to, this is a direct strain sigma 2 by A, it is there now. Sigma 2 is representing the longitudinal stress divided by n smallest. This is known as longitudinal stress, but because of remaining tensile as well as hoop stress as well as the radial compressive stresses, that the lateral stresses are so developed but in opposite directions. But according to our previous discussions, hoop tensile stress is the tensile stress. Hence, the opposite direction is that is diameter is decreases now. Hence, we are taking that is the longitudinal strain is decreases. It can be written as negative way sigma x divided by ME. Again, tensile radial compressive stress is there, compressed in nature, but lateral strain is affected in the opposite direction, that is the expansion is taking place. Hence we are taking it is equal to positive Px divided by Me now. This is known as a total longitudinal strains that is induced at a distance of X from the center of the cylinder. Since the longitudinal strain is a constant that is independent of distance x according to the Lamis equations, hence the above equations sigma by 2 by minus of sigma x by me plus px by me, it is treated as a constant. This constant assume just it is represented as a 2a now. That is here sigma by 2e it is constant now. This value is constant. The remaining values are there now. Minus of sigma x by me plus px by me is equal to constant. That me is again constant now. So the remaining values is sigma x minus px. It should be constant now. The constant it is equal to, we are considering it is equal to 2a now. So it can be represented as the sigma x is equal to p plus 2a. This is the equation number 4 now. So equating these values of sigma x from the equation number 3rd and 4th when we are taking, that is px plus 2a is equal to minus of px minus of x dpx divided by dx now. From this relation now, dpx divided by dx is equal to, so when we are taking outside, the remaining values are there now. Here minus px plus px is there now, and so we are taking this toward the right side, minus of 2, just when you are taking common word, px plus here a by x now. From this relationship we got to minus of 2px plus a divided by x now. This integrating these equations on both sides, we are having log of px plus a is equal to, because it is equal to dpx divided by px plus a is there now. The integration is equal to log e px plus a. It is equal to minus of log of a now x, because dx divided by x integration is equal to 1 log x. Here minus it is there, plus some integration constant required, just I'm assuming it is equal to log e b now. So from this relationship we can write it now, bx plus a is equal to b by x square now, because just when I'm taking minus and nothing but 1 by x, 2 is there x square now. Here b is there now, it can be written as now p by x square, or px is equal to b by x square minus a now. This is the equation number 5th. By substituting the values of this px in equation number 4, we are having sigma x is equal to b by x square minus of a plus 2a, or it is equal to b by x square plus a now. That is from this equation we got, one equation is px is equal to b by x square minus a. The second equation is sigma x is equal to b by x square plus a. These two equations are representing how that radial stress as well as the circumference stresses that are changing with respect to the radius x. These two are important and it is also representing how that they are variating from internal radius to outer radius. This a and b are known as the integration constant that are evaluated based on the condition of the cylinder, how the pressure is acting now. So the values of a and b in the above equations are evaluated from the given conditions. The above two equations 5 and are known as Lamis equations now. You should be remembered that the values of px is compressed in nature and sigma is intensile in nature now. The intensity of pressure outside of the cylinder, here outside here, the intensity of pressure, it is now treated as equal to 0 now. That is nothing but R two values now. Similarly, internal outer radius is equal to R1 is there, PR1 is equal to 0 now. Though it has some hoof stress due to pressure inside the thick cylinder. So these are the assumptions what we made according to Lamis theory in order to identify how the pressure distribution, that is how the radial stress as well as the hoof stresses that are induced within it now. So these are the reference books as well as the test books are taken to collect the above materials. Okay, thank you.
Like, share and subscribe. hit the bell icon for more updates.